This is important for all science classes you ever take ever. You should know this. In general, as things get smaller, their surface area to volume ratio gets bigger. And for cells in biology, high surface area to volume ratio is a good thing. I would know that one of the biggest goals that a cell has is to keep its surface area to volume ratio very large. It wants that number to be as big as possible, which means the size of the cell wants to be as small as possible. The smaller a cell can be, the happier that cell is. Because as a cell gets small, its surface area to volume ratio gets really big. We're going to do a math problem together. Ready? I would go through this with me if I were you. Okay. What we're going to do is we're going to imagine a cell that's shaped like a cube. Okay, because cubes are easy to do surface area and volume measurements with. So here's our original cube. And this is a cell. It just happens to be a cube-shaped cell.
Is that a thing?
Is what a thing?
Cube-shaped.
Oh yeah, you've got cells that are called cuboidal epithelial cells.
What?
They're shaped like cubes.
You say cube cell. Oh. It was close though.
Relax, they're shaped like cubes. Imagine, if you will, we've got this box-shaped cell, okay? And this box-shaped cell is, let's say, 2 units by 2 units by 2 units tall. It's a true cube. Okay? Which would mean that on this cell, if I'm let's say we got the blood going by here, there's a blood vessel that cruises by the cell, and next door to this cell it would have other cell neighbors on top of it and beside it and whatever, but at least one surface would be exposed to the blood. So here's blood cruising by. If I'm oxygen in the blood, I can scoot through the cell membrane directly into the cell, right? And does the cell have waste building up in it? If it's a living cell? Sure, like what kind of wastes? Probably some spare water. Carbon dioxide is coming out of the cell. It's going to get dumped back into the blood through the cell membrane. The point I'm trying to make here is that this little cube-shaped cell wants to have a lot of its surface exposed to the blood because it can move stuff in from the blood and move stuff back out to the blood if it's got lots of surface exposed to the blood. That's why this whole surface area business is important to cells. All right, so watch. What's the cell want again as far as surface area to volume ratio goes? It wants surface area to volume to be, it wants the surface area to volume ratio to be very high. So let's take a look here. First, let's calculate surface area. Ready? Follow along, do the math, because I'm going to ask you to do it on a test. Surface area equals length by width by, how many sides does the thing have? 6. Okay. Now fill in what I know. Length is 2 units. Width is 2 units. And it has 6 sides. Equals 2 by 2 is 4. 4 by 6 is 24 units. Is the surface area. What's the volume of this box that we just drew? Yeah, it's going to be 2 length. No, wait a minute. Let's not do that. It's length by width by height. Okay. So now I fill in what I know. Length is 2. By width is 2. By height is 2. 2 by 2 is 4 by 2 is 8. So now if I want to figure out surface area to volume ratio, I do this. Surface area. Are you familiar with this? The surface area and then a colon and then volume would be surface area to volume ratio is how math nerds would look at that. Okay. Surface area to volume ratio equals surface area divided by volume. So now I'm going to fill in what I know. What was my surface area? 24. Divide by 8. I get a surface area of 3. or surface area to volume ratio, excuse me, of 3. Everybody understand how I did all the parts of that? First I figured out surface area, then I figured out volume, then I divided surface area by volume, and I got to 3. If I want that surface area to volume ratio to get bigger, what could I do to the size of the box? Yeah, make it smaller.